and creep in structural materials. Welcome to Blueprint to Reality, where we break down complex engineering concepts into easy-to-understand lessons. In this episode, we'll dive into fatigue and creep, two crucial phenomena that affect the longevity and safety of materials used in structural engineering. What is fatigue? Fatigue is the weakening or failure of a material due to repeated loading and unloading cycles, even if the loads are below the material's yield stress. Over time, these repeated stresses can cause small cracks to form in the material. These cracks grow incrementally with each load cycle, eventually leading to catastrophic failure. For example, think of bending a paperclip back and forth. Even though the paperclip is not under extreme stress, the repeated motion causes the material to weaken, and eventually, it breaks. This is a simple example of fatigue failure. In real-world engineering, fatigue can occur in structures like bridges, airplanes, or machinery, where components experience repeated loading due to traffic, wind, or operation. Why does fatigue matter in structural engineering? Fatigue is crucial to understand because materials may appear to be in good condition based on a one-time test or inspection. However, over time, repeated loading can cause cracks to form and grow, leading to unexpected failures. Engineers must design structures to withstand these cycles of loading and unloading. This includes ensuring that materials used in key components are resistant to fatigue and that the structure as a whole can handle dynamic forces like wind, traffic, or vibrations. What is creep? Creep is the gradual, time-dependent deformation of a material under constant stress, typically at elevated temperatures. Unlike fatigue, which is related to repeated loading, creep occurs when a material is subjected to a continuous load over an extended period. For example, imagine placing a heavy weight on a rubber band and leaving it for hours. Over time, the rubber band will stretch and elongate, even though the load is constant. This is similar to how creep affects materials at high temperatures or under constant pressure. In structural engineering, creep is particularly important in materials like steel, concrete, and polymers, especially in applications where components are under continuous load, such as in high-temperature environments like power plants or in concrete structures subjected to sustained loads over years. Why does creep matter in structural engineering? Creep is important because, over time, the material will continue to deform, which can cause failure if not properly managed. Structures that experience high temperatures or long-term stresses, such as nuclear reactors, turbines, and bridges, must be designed with materials that can resist creep. If creep is not considered, it can lead to issues like 1. Distortion of structural components. Over time, components can elongate, bend, or change shape, compromising the integrity of the entire structure. 2. Loss of load-carrying capacity. As materials deform under sustained load, they lose their ability to carry loads, which can lead to structural failure. How do we measure fatigue and creep? Both fatigue and creep are typically measured using specialized tests. 1. Fatigue testing. In fatigue testing, a material is subjected to repeated loading cycles at various stress levels. Engineers track the number of cycles it takes for cracks to form or the material to fail. This is used to establish a fatigue limit for materials, which is the maximum stress level below which the material can theoretically withstand infinite cycles without failure. 2. Creep testing. In creep testing, a material is subjected to a constant stress at an elevated temperature over an extended period. Engineers measure the strain or deformation over time to determine the material's creep rate and predict how it will perform under long-term loads. Both tests help engineers determine how materials will behave under real-world conditions, ensuring the structural components will last for their intended lifespan. Fatigue versus creep. Key differences. While both fatigue and creep lead to material failure, there are key differences between the two. Loading type. Fatigue is caused by repeated loading, while creep is caused by constant loading over time. Time frame. Fatigue leads to failure after a relatively short period due to cycling stresses, while creep develops over a much longer period under continuous load. Temperature sensitivity. Creep is more significant at high temperatures, while fatigue can occur at ambient temperatures but is also influenced by vibration or dynamic forces. Real-world applications. In aerospace engineering, fatigue is a significant concern. Airplanes experience constant vibrations and pressure changes during flight, which can cause fatigue failure in critical components like wings, fuselages, or landing gear. Engineers use fatigue-resistant materials and design strategies to ensure the airplane can withstand millions of flight cycles without failure. In civil engineering, creep is a concern for long-term structures like bridges and concrete buildings. Concrete, especially when subjected to high loads over extended periods, can undergo creep, potentially causing deformation and damage to the structure. Engineers often use reinforced concrete and carefully manage the load distribution to minimize the effects of creep. Similarly, in power plants, materials like turbines and pipes are subject to high temperatures and continuous stress, making them susceptible to creep. Engineers select materials with low creep rates and carefully monitor their performance to avoid failure. Conclusion. In summary, both fatigue and creep are important factors that influence the durability and safety of materials used in structural engineering. Fatigue arises from repeated loads and can lead to cracks and failure over time, while creep is a gradual deformation caused by sustained loads at high temperatures. By understanding these phenomena and accounting for them in material selection and design, engineers can create structures that are both safe and long-lasting, ensuring their performance even under challenging conditions. Thank you for tuning in to Blueprint to Reality. If you found this explanation helpful, don't forget to like, share, and subscribe for more civil engineering insights. See you in the next episode. Types of soils and their properties. Welcome to Blueprint to Reality, where we explore key concepts in civil engineering and construction. In today's video, we're diving into an essential topic: the different types of soils and their properties. Understanding soil types and their behavior is critical for ensuring that structures are built on stable, strong foundations. Let's explore the key types of soils and how they impact construction projects. Introduction to soil types. Soil is a complex material made up of mineral particles, organic matter, air, and water. Different types of soil are categorized based on their texture, structure, and composition. The most common types include sand, silt, clay, and loam, each with its own unique properties that affect its suitability for various construction projects. Let's break down each type and its properties. Sand soil. Sand is one of the coarser soil types, made up of large particles that don't retain much water. This makes sand soil excellent for construction because it provides good drainage and compaction. Some key characteristics of sand soil are granular texture. Sand particles are large and loose, making it easy to compact. High drainage. Sand allows water to flow through it easily, preventing water accumulation. Low plasticity. Sand doesn't easily mold or retain shape when wet. Sand is ideal for foundations where water drainage is a concern, such as in areas with high rainfall or near bodies of water. However, its low cohesion means it may not be suitable for supporting heavy structures without proper foundation support. Silt soil. Silt is made up of finer particles than sand but coarser than clay. Silt has a smooth texture and retains moisture well, but it's also prone to erosion when wet. Key properties of silt soil include fine particles. Silt particles are small, often making it more prone to compaction. Moderate drainage. Silt doesn't drain as well as sand, leading to potential water retention issues. High plasticity. Silt can be molded and shaped when wet, which makes it more flexible than sand. While silt can be good for plant growth, its poor drainage and tendency to shift under pressure can make it less reliable for construction without soil stabilization techniques. Clay soil. Clay is made up of the smallest soil particles and has a sticky, dense texture when wet. It's known for its ability to hold water and its high plasticity, which allows it to be molded easily. Some key properties of clay include fine, dense particles. Clay particles are very small, leading to its characteristic smooth feel. Low drainage. Clay retains water, making it less ideal for areas prone to flooding or moisture buildup. High plasticity. Clay can easily be molded into various shapes when wet, making it useful in construction but also prone to shifting and cracking when dry. Clay is often used in brick making and ceramics, but in construction, it requires careful engineering to ensure it supports structures properly. Engineers must account for its potential for expansion and contraction with moisture changes. Loam soil. Loam is often considered the ideal soil for construction because it contains a balanced mixture of sand, silt, and clay. Loam has the best of all worlds: good drainage, compaction, and moisture retention. Some characteristics of loam include balanced texture. Loam's mixture of sand, silt, and clay makes it ideal for building, as it provides adequate drainage while retaining moisture. Good compaction. Loam can be compacted well to provide a solid foundation for structures. Moderate plasticity. Loam has enough plasticity to be molded, but isn't as prone to extreme shifts as clay. Loam is highly sought after for construction projects because it combines the best qualities of sand, silt, and clay, making it perfect for stable foundations and gardens. Peat soil. Peat is a unique type of soil rich in organic material, often found in marshy areas or bogs. It is composed of decayed plant matter and is generally not ideal for construction due to its low stability. Key properties of peat include high organic content. Peat contains a high amount of decayed organic matter, making it less stable than mineral-based soils. Low strength. Peat is weak and compressible, making it unsuitable for supporting large structures. High moisture retention. Peat holds a large amount of moisture, which can lead to instability. Peat requires significant soil treatment or reinforcement before it can be used for construction, such as soil stabilization or deep foundations. Importance of soil testing in construction. Understanding the properties of different soil types is vital for ensuring a stable foundation for any structure. Soil testing helps engineers determine the best methods for foundation design and construction. Some common tests include Standard Penetration Test. SPT measures the resistance of soil layers to penetration, helping engineers assess soil strength. Atterberg Limits Test determines the plasticity and shrinkage of clay and silt. Permeability Test measures how easily water can pass through soil, which affects drainage and stability. Challenges with different soils. Each soil type presents its own challenges for construction. For example, sand. While easy to compact, sand can shift under heavy loads without proper foundation support. Silt. Prone to erosion and swelling, which can lead to foundation issues. Clay. Can cause problems with expansion and contraction, leading to cracks in foundations. Peat. Due to its high organic content, peat lacks the stability needed for most construction projects. Conclusion. The importance of understanding soil types. The type of soil at a construction site has a significant impact on the design and success of a project. Engineers must thoroughly understand soil properties to ensure the stability and safety of the structure. By testing and analyzing different soils, sand, silt, clay, loam, and peat, engineers can make informed decisions about the best foundation design, material use, and construction techniques. Proper soil assessment ensures that buildings, roads, and other structures are built on solid ground. Thanks for watching Blueprint to Reality. Don't forget to subscribe for more insights into civil engineering and construction.